we're going to talk about effect size and power. So effect size and power are two things you need to think about whenever you do hypothesis testing. So first, effect size. Well, we're going to talk about what effect size is by contrasting it to the t statistic. They actually have a lot in common, but there's just one subtle difference that makes a huge difference. Then we're going to talk about the rules of effect size and why we need effect size. Then we're going to talk about power. What is it? Why do we need it? And how do all these different things affect power? For instance, sample size, effect size, variability, and alpha, the significance level. Okay, so first things first, just a review of what the sample t really means, right? So a lot of times people just memorize the t formula, like it is, the x bar minus mu over standard error, right? But think about what this actually means. So t equals x bar minus mu over the standard error. And I'll write that as s sub x bar. What this will end up giving you is this distance, right? So the distance between your sample and your hypothesized mu. And when you divide it by standard error, you get how many standard errors you need in order to get from x bar to your mu. So you get distance in terms of standard error. So distance in terms of standard error. And you want to think of in terms, sort of like instead of using like feet or inches or number of friends, we get distance in the units of standard error, right? So whatever your standard error is, for instance here, that looks about right? Because this is a normal distribution. This should be about 68%, right? So that's a standard error, right? Your t is how many of these you need in order to get to t. So this might be like a t of 3.5. 3.5 standard errors away gets you from mu to your sample difference. And so this is the case of a two-sample t-test, right? So independent samples or paired samples, where we know the mu is 0. So this is sort of the concept behind the t statistic. Now, here's the problem with this t statistic. It's actually pretty sensitive to n. So let's say you have a difference that's very, very, that's going to stay the same. So a difference between, let's say 10 and 0, right? So we have that difference, right? If you have a very, very large n, then your SDOM becomes a lot skinnier, right? And because of that, your standard error is also going to shrink, right? So the standard error shrinks as n shrinks. And because of that, even though we haven't changed anything about this mean, about this x bar or mu, by shrinking our standard error, we've made our t quite large, right? So we've made our t like all of a sudden we're six standard errors away, but I really haven't changed this picture, right? So that's actually a problem that t is so highly affected by n. The problem with that is that you could artificially make a difference between means look statistically significant by having a very, very large n. So we need something that tells us this distance that's less affected by n, and that's where effect size comes in. So in effect size, what we're doing is we want to know this distance in terms of something that's not so affected by n. And in fact, what we're going to use is the population standard deviation. Because let's think about t. So that's x bar minus mu over standard error, right? So this contrasts that to looking at the distance in terms, not of standard error, but in terms of the standard deviation of the population. What would that look like? Well, we could actually derive the formula ourselves. We want that distance in terms of, number of inches or number of problems correct or whatever the raw score is, right? Over, instead of standard error, we would just use the S. Or if you had it, you would use sigma. So this is you could think of this as the estimated sigma, right? And this is like the real deal sigma. And that's what effect size is. And effect size is often symbolized by the letters D and G. D is reserved for when you have sigma. G is used for when you use S. All right, now let's talk about the rules of effect size. Well, the nice thing about effect size is that the n doesn't matter as much. Whether you have a small sample or a large sample, the effect size stays similar. In test statistics such as T or Z, the n matters quite a bit. And let's think again about why. So in the T statistic, I've been writing it so far as over standard error, but let's think about what standard error is. Standard error is S divided by the square root of n, right? Now as n gets bigger and bigger, so let's think about n getting bigger, this whole thing in the denominator, this whole idea, this whole thing becomes smaller and smaller, right? And when you divide a positive, or doesn't matter, negative or positive, if you divide some distance by a small number, then you end up getting a more extreme value. More extreme. So by more extreme, I mean way more positive. All right, more positive. More on the positive side, or way more negative, right? So the T statistic is very, very sensitive to n, and so is the Z, because Z, the only difference is instead of S, we use sigma, right? And so the same logic applies. But for effect size, D and G, we don't divide by square root of n. So in that way, n doesn't really have as much of a bearing. Okay, so one thing to remember is if you know sigma, use Cohen's d. If you need to estimate the standard deviation from the sample, S, you want to use Hedges G. Okay, so now we know what effect size is, and it's nice that it's not as affected by n, but why do we need it? Well, effect size is what we use, the statistic we use, to interpret practical significance. So for instance, we might have some sort of very small difference between group 1 and group 2. So let's say males and females on some game or task have a very, very, very tiny, tiny difference. Like, let's just say males are ahead by 0.0001 points, right? And practically, sort of doesn't matter, right? But if you have a large enough effect size, if you have a large enough n, you could get a small enough standard error that you could make that tiny difference seem like a big deal, right? And you can imagine that would be a sort of odd situation. We take a difference that sort of doesn't matter, but then make a big deal out of it because of some fancy statistics we did. Well, the effect size isn't going to be affected by n, and so that's going to give you a more straightforward measure of, is this difference big enough for us to sort of just care about, period? It's not going to tell you whether it was significant or not based on hypothesis testing, but it's going to give you the idea of practical significance. And here we're using the modern term for significance, as in importance. It'll tell you of its practical importance, not statistical outlierness, right? That's not what it's telling you. It's talking about just regular old practical importance. And the way you could think about this is just thinking about it as, is this difference worth noticing? Is it worth even doing statistics on? The thing about hypothesis testing is that it could be deceiving. A very, very large sample size can lead to a statistically significant, one of these outlier differences that we really don't care about, that just has no practical significance. So here, although we've been trying to talk about this again and again, trying to sort of clarify that statistically significant doesn't mean important, it just means it lies outside of our expectations, right? It's important to realize once again that statistical significance does not equal practical significance. This is sort of talking about how important something is, right? And this is just sort of saying, does it stand out? Does our X bar, or sample, actually stand out? Okay, now let's move on to power. What is power? Well, power really needs to go back to our understanding of the two types of errors. Remember, in hypothesis testing, we can make an error in two different ways. One is the false alarm error, and we set that false alarm error rate by alpha, right? And the other kind of error is this incorrect decision that we can make called a miss. A miss is when we fail to reject the null hypothesis, but we should have. We really should have. So dang it, we missed it, right? And that's signified by beta, by the term beta. Now, when the null hypothesis is true, then we can know if we already set our probability of making an incorrect decision, just by subtraction, we can figure out our probability of making a correct decision, right? So if our probability is 0.05 in making an incorrect decision, the other possibility is that we make a correct decision, 95%, 1 minus 0.05. In the same way, when the null hypothesis is actually false, we could figure out our probability of actually making a correct decision by just subtracting our probability of making an incorrect decision from 1. So this would be 1 minus beta, right? In that way, these two decisions that we make, they add up to a probability of 1. And these two decisions that we can make add up to a probability of 1, right? But in reality, only one of these worlds is true. That's why they both have a probability of 1. We just have no idea whether this one is true or this one is true. And no one can ever really say. But that's a philosophical question. All right. So given this picture, power resides here. And this quadrant is what we think of as power. Now, power is just the idea, given that the world is actually false, right? That's this world we live in. Pretend we've ignored this part, right? So I'm just gonna ignore this entire world, right? Given that this null hypothesis is false, what is our probability of actually rejecting the null hypothesis, right? And that is what we call power. So think of this as the probability of rejecting null when the null is false, given the null is false.